Hello, my name is Marco Arruda and welcome to this ROS video tutorial. Actually, this video is the first part of a series of videos and I'm calling it Exploring ROS using a two-wheeled robot. Okay, so for this first video I'm going to start explaining what this is going to be about. Okay, so first of all we are going to explore the tools and features that ROS can provide for us using a two-wheeled robot. But why a two-wheeled robot? So basically this is a very simple model of a robot. One of the robots I really like to work with because we can do a lot of real cool stuffs in robotics using a very simple mechanism, a very simple locomotion mechanism. So we don't have to care a lot about the locomotion of the robot, the problems with the mechanisms, so we can focus only on the robotics applications. Okay, and also we are going only simulating robots here in this tutorial, but we are gonna be very close to real robots, the ones that we can mount ourselves buying spare parts, very cheap projects on the internet, for example. Or if you prefer, you can also buy a robot off the shelf like the Pioneer, Turtlebot 2 or Turtlebot 3. So this kind of robot is very common to be found in the world. Okay, so in order to start to do all these tutorials, we are going to use the RDS, ROS Development Studio, provided by the Construct. After all, you can do everything using only our web browser. And of course this is free. So if you don't have an account yet, you can create a new one and start using the system for free. You just need to follow the link at the description of this video and you'll be able to see the same screen I'm showing to you right now. Okay, so we have public projects here and you can follow as example in other moments, but for instance we are gonna create a new project. Okay, so I'm gonna call it Exploring ROS with a two-wheeled robot. Okay, I'm gonna put the same for the description, and this is a private project. I'm gonna share the source code later, so I don't need to share these files here using the RDS, for instance. Okay, so let's create a project, and it's ready to be opened. So let's open here and wait a few seconds until we have our ROS environment ready to be used. Okay, so here we are inside RDS desktop. We have some tools here and some simulations that can be used. But actually, for this first video, the main goal of this video is to build our own robot. Okay, so in order to do that, I'm gonna explain very quickly about the URDF and XACROS files, and then we are going to use the RViz tool to visualize the robot we are going to create. Then we are going to insert this robot in a Gazebo world, which is the simulator we are going to use. Okay, and then after all we are going to interact with the simulation with the robot we have just created. We are going to control the robot using a Gazebo plugin to move the robot around the simulation scenario. Okay, so basically let's take a look in the structure of a two-wheeled robot, and actually this is a very simplified structure just to have a very simple point to start with. Okay, so we are going to start with only 3 parts of the robot. The main part, of course, is the chassis of the robot, so that's the biggest part of the robot, and where we are going to place the other parts. Okay, we're going to mount the other parts in the robot. So the parts of the robot are called links. So we have here the chassis is a link, the left wheel and the right wheel also, they are links of the robot. And in order to put everything together, we have to use joints. Here in blue you can see we have 2 joints to assemble the left wheel and the right wheel. Okay, so let's start here in RDS creating a new package for our robot. Okay. But before, let me explain very quickly about the RDS project structure. So we have basically two ROS workspaces, and here they are called CATKing workspace and simulation workspace. We have also this notebook workspace, but actually it's not a ROS workspace. It's just to keep the files of the Jupyter notebook. We are not gonna use it in this video, but it can be useful in the future. Okay. So as we are going to create a new robot and we want to use this robot in a simulation, we have to create our package inside the simulation workspace. Okay. So let's open here the terminal. I'm gonna get inside the simulation workspace, source folder, and CATKing create package. My two-wheeled robot, I'm gonna call it description, and it depends only on a URDF. So here we have new package, and let's start creating a folder here called URDF, and that's the folder we're gonna put the files that describes the robot. Okay. So let's start creating the main file of the robot, and I'm gonna call it my two-wheeled robot.XACROS, which is the extension we are going to use. So what is XACROS, this XACROS extension? Basically, XACROS is an acronym for XML macros. Okay, so a macro is something used to do repetitive tasks, let's say, but actually we are trying to repeat the same code more than once. So we are going to use a macro, just change some parameters. Okay, in this case, for example, we can use a macro to create the left and the right wheel. After all, they are going to be equal, but of course the right wheel is on the right side of the robot and the left wheel in the other side. Okay, that's why a macro can be useful for us, and that's why it's called XACROS XML. The kind of the format of the file we are going to use to describe the robot, and macros to use these features. Okay. Actually, for this first video, we are not going to use macros yet. We are going to do this in the next step, in the next video. But for now, we're gonna work with the only URDF. Okay, the Unified Robot Description format to describe our robot. But we are going to work already with a XACROS file. Okay. So let's start creating the links of our robot, starting by the chassis. Okay. I'm not gonna do everything from the scratch. I have something kind of ready here with me, and we can start using it just to make it more quick and not so boring for you. Okay. So first of all, this is an XML file. So we have to declare right here at the beginning of the file. Let's put here for the editor, this is XML, so we can have the colors in the test. It's easier to see. Okay, so we are describing a robot. So the first tag we are going to use is this tag called robot. Let's close it, and everything about the robot must go inside the robot tag. Okay. So we have to declare here the name of the robot. So in this case, I'm calling it my two-wheeled robot, like this. And we have also to define this is a XACROS file. Okay. So let's start creating the main link of the robot, which is the chassis. I'm gonna copy and paste here and explain what does it mean. So we have here this tag called link, because we have a link of the robot. This is very easy to understand. So we have inside the link some basic properties that are mandatories. So we have to define the pose of this link. For instance, we are defining here, we have X, Y, and Z, and then roll, pitch, and yaw. Okay, we are defining everything 0 except Z, because we don't want the chassis to touch the ground from from the beginning of the simulation, okay? And then we have to define the inertial properties. So we start telling the mass of the object. So we are putting here just 5 kilograms, just to have something good value to work with. And then the origin of the mass. Okay, so we are going to use the same origin we are using for the pose of the link. And then the inertia matrix. So we need 6 values here. I'm not going to show how we can calculate this. There's a very good reference also in the description of this video. You can follow if you have doubts about how you can find these values. Okay. So after the inertia, we have to define also this collision property, which is basically telling the simulator the dimensions of this object, the dimensions that must be used to calculate the collisions when this object, after all, this object can collide with other objects in the scene. Okay, so inside the collision we have only this geometry property, and for the chases we are defining this is a box, and the dimensions x, y, and z again. Okay, we close the properties, geometry and collision, and we go to the visual property, which is basically almost the same of the collision, but actually it's not used by the simulator to calculate the collisions between objects, but used to generate the visualization we are going to have of the object in the simulator. Okay, so this is just the visual of the object for the user, but it's not important for the dynamics of the simulation. Okay, so for this, for instance, we're gonna use the same values of the collision, so we can have this. We are looking at the same object we have colliding in the scene. Okay, and we are also defining here this property material with this name blue, which is basically just a color to put in the material. Okay, we have to define later this material here, and we are gonna get there. So after having the main body of the chases, we have to define also the caster wheel. So as you can see here, the robots have to have this caster wheel to have 3 points touching the ground, so the robot won't be falling and kicking on the ground all the time. Okay, and we are defining it not as another link. We could do this as another link here in the front of a robot, but to make it easier at this first moment, we can just define here together with the chases. Okay, so we are defining all the collision of the caster wheel. So we have also to define the origin, rho, pitch, and yaw, x, y, and z. The geometry, this is a sphere, and that's the radius of the sphere. Okay, and this surface property is basically used to define the forces between the surfaces. After all, the caster wheel is touching the ground, so we have to define the forces between them. In this case, this is 0, and this is the property just to tell that they are going to have no forces between these two surfaces. Okay, and final thing, the visual of the caster wheel, which is basically the same we have done here. We are doing for the caster wheel, so defining the same geometry we have defined for the collision to the visual property. Okay, so this is a wheel, the same origin, and the same radius for the sphere. Okay, so let's go to the next link. Let's create first the right wheel. I'm gonna break some lines here just to see it clear. So we have link right wheel, we have the inertial again, the collision, and visual. This is just the most basic properties, but here we are defining the geometry as a cylinder. Okay, of course, because this is a wheel. So in order to have the right wheel attached to the chases, we have to create a joint. Okay, so I'm gonna paste here the joint of the right wheel. So joint right wheel, I'm calling it, that's the name. And the type of the joint is continuous. We are going to explore more types of joint in next videos, but for instance, let's just bear in mind that a wheel is a continuous joint. Okay, so we have also to define the origin, and that's exactly the position we are going to place the wheel in the chassis. This property child, it's very important that the child link property must be exactly the same we are using here, the link name, okay, and the parent link, exactly the same name we are using for the chassis. So link chassis must be the same name, otherwise it's not gonna work. Okay, the axis where this joint is gonna rotate around. Okay, so we are not displacing it in the angles, but defining only the axis. So in this case, it's rotating over the y-axis. Okay, and some efforts, just some values to make everything work here. You can play with these values later to see how the robot behaves. Okay, and the joint properties, damping and friction. Okay, so let's do the same for the left wheel. I'm not gonna explain again because we are doing basically the same thing for the left and the right wheel. Basically the big difference is the position of the joint. After all, we are reflecting the joints. One wheel is placed on a side of the robot, and the left wheel placed on the other side of the robot. So the Y position here, we have a positive value here, and for the left wheel we have a negative value. Okay, so basically that's it. And now we have to define also the materials we are using. So let's put here, we have some definitions to have here, so we can play with some colors. Okay, so materials properties are used by RViz, so that's why we are defining here some colors using this tag material, and other colors here using Gazebo material, because this one is used by the simulator and this one is used by RViz. Okay, we cannot use the same tag for both of them. So now we have the URDF ready to be used, and now we can visualize our robot using the RViz tool. Okay, so in order to do that, let's create a launch file, because we are gonna launch RViz and also define our robot. I'm gonna create here a folder called let me change it here, a folder called launch, and a new file called RViz launch. Okay, inside this file I'm gonna just paste what I have here, and I'm gonna explain what this means. So we are defining here the robot description parameter, ROS parameter, and we are using, actually I'm using here a XACROS command to convert my XACROS file to URDF file, but actually in this case we are not using macro commands here. Okay, so we don't have to use this conversion. I'm just gonna use this cat command, okay, just to read the file. Let's just change the name of the file. This is my two-wheeled robot XACROS file. Okay, inside my two-wheeled robot description package. Okay, and the same here at the end of the file. So we are also publishing the joint state of the joints of the robot and the robot state publisher. Okay, and final thing, starting RViz using the argument, passing the package as an argument. Okay, so let's launch it. First of all, let's compile the package just to generate the package header files, and we're going to be able to choose the auto detection for our files inside this package. Okay, great. Now let's source Devil folder and ROS launch my two-wheeled robot description, RViz launch, Okay, so now we have RViz running. In order to see RViz, to use RViz, we have to open these graphical tools. Let's put it to the right side, make it a little bigger. Wait a few seconds. Okay, so here we have RViz running, and now we can configure it to see the robot model. So I'm gonna click here to add a new visualization tool, and I'm looking for the robot state visualization. Okay, so I'm gonna select here and click OK. And here we have the robot, okay, because the robot state visualizator is taking the value, the description of the robot from this ROS parameter called robot description. The same we have configured here in the editor. Let me increase the font size. Here, robot description, the same name we are reading in RViz, okay. So here we have the robot. As you can see, we have 3 links. So we have the main body, the chassis, and the caster wheel we have added. So the chassis is in blue and the wheels in red, so we have 3 links. You can see here in RViz the links, okay, and the properties of each one, okay, and basically that's it. You can use this tool. It's a very good tool. It's not heavy, it's very easy to use, and you can use to visualize the robot as you are developing and creating, describing the robot in a URDF file. Okay, so let's go to the next step. Now I'm gonna launch a Gazebo simulation. Okay, so we can choose here in RDS a lot of simulations, but for this example I'm gonna use just an empty world because we have our own robot, and I just want to see my robot in an environment. Okay, so let's close RViz, we don't need it anymore, and close the graphical tools. And in our IDE, okay, just a few seconds. So here we have the empty simulation, it's running. Okay, it's working. So let's add the robot, let's put the robot inside the simulation. So in order to do that, I'm gonna create another launch file. I'm gonna call it spawn.launch because we're gonna use the spawn task of the spawn service of Gazebo to put the robot inside the environment. So let me copy the content I have here and paste here. Okay, so again, this is just another XML file. We have the same instruction as before. We have the launch tag because this is a launch file. Okay, and first the parameter, we are using robot description. Let's use the same instruction we have used here for RViz. Okay, so we are just reading from this URDF file, the URDF description inside this XACROS file. So let's just paste over this instruction. And I'm defining 3 arguments here, X, Y, and Z, which are the position, which is basically the composition of the initial position of the robot in the environment. Okay, and here I'm creating this node called my two-wheeled robot spawn. It's just a node that's gonna execute the task to spawn the robot inside the environment. And it comes from the package called Gazebo ROS. The executable is called spawn model. We are gonna see the log of this task of this node in the screen in the same log of the simulation. And as arguments we have here, we are using, let me break the line so I can see more easier. We are passing as argument URDF because this is a robot described using URDF language format, okay? And as parameter we are using robot description, which represents the description of the robot you have just created. The name of the model, I'm gonna call it again my two-wheeled robot. And using the arguments we have just defined it here, okay? We are defining here because if you want, if you prefer, you can change these values in the command line when you called the ROS launch file. Okay, so we are just passing the arguments here. So let's do that. We have the simulation on the right side, and on my left side I have my terminal. Let me clean it and launch my two-wheeled robot description, spawn launch file. Let me open the log so we can see the result. Okay, so here we have the robot, and as you may have noticed, we are not seeing the same colors you have defined for RViz, of course, because they don't use the same color definition. So for Gazebo we have defined the chassis as orange and the wheels as blue. Okay, and to execute the final step of this video, we have to control the robot. Okay, and in order to do that, I'm gonna just close this. I'm gonna just get back to the editor here, because we have to add one more thing to make this robot controllable by ROS. Okay, so we have to use a Gazebo plugin. Let me just copy here and paste right here with the other Gazebo instructions. So we are using this Gazebo plugin called Differential Drive Controller. Okay, this is a very simple plugin, and actually it's just was made for controlling and sending twist messages, which means linear and angular velocities to a differential drive robot. Okay, so we have some parameters here. We are not using legacy mode. We are setting the plugin always on, so it's always working. That's the update rate, the rate that we are sending the messages. So we have to define here the left joint. So that's very important. You have to use the same name we have defined here for the joint. Okay, so joint left wheel and joint right wheel. Okay, the distance between the wheels. So we have here 0.2, which is actually it's 0.3. So let's fix it. And the wheel diameter. So we have here in the wheel we have a cylinder with radius 0.1, so the diameter is just 2 times this, so it's correct. And the torque, this is just a good value for this robot of this size and its weight. You can play with this value to see what happens and see the changes in the behavior of the robot. Okay, and we are also defining the name of the topic which the plugin is going to listen. So we are defining here command velocity, and the odometry topic, which is the topic the plugin is going to publish the odometry values, okay, from the simulator to ROS. And also odometry frame, it's creating a frame to ROS messages, so you can use TF to do other stuff using the same data which is coming from the plugin. Okay, and finally the base frame. Here it's defined chassis, but actually the name of our frame is link chassis. Okay, so let's change it here. And let's take a look on the simulation again. Let's relaunch it, because we are going to spawn the robot again, so I want to have the simulation cleaned. Let's wait a few seconds until the environment's ready. In the meantime, let's prepare the terminal. So ROS launch my two-wheeled robot description package, that's the package name. Now we have the spawn launch file. So great, the simulation is ready. Let's launch the robot. Let's check the log. So great, here we have the robot was spawned, and we have it here in the simulation in the empty scenario. Okay, the caster wheel, two wheels, and the chassis, everything as expected. And let's check the topic list. We have here command velocity, ED odometry. So let's move the robot around. So let's use this package here, teleop twist keyboard. Okay, and you can use your keyboard to move the robot, because we are sending twist messages to Gazebo, and through the plugin Gazebo is taking these messages from ROS and converting to torque for the wheels. Okay, so here we have the robots moving, and you can play with the variables here like torque and wheel separation, wheel diameter, and to see how this affects the robot behavior. Okay, so I hope this video could help you to understand how it works, the robot description, URDF format, Gazebo plugins, and the RViz tool to visualize everything. And don't forget, if you like this kind of video, don't forget to subscribe to our channel and press the bell just beside of the subscribe button to be notified about the videos we publish every day. Okay, see you in the next video. Thank you.